In Chapter 11, our focus is going to be on the use of Taylor polynomials. And Taylor polynomials are created from a special series that we're going to talk about now, which is our power series. And these polynomials are basically used to approximate values of functions. So let's look at our power series. Our first power series is this summation from k is equal to 0 to infinity of c sub k times x to the k. And it expands out to c sub 0 plus c sub 1x plus c sub 2x squared, and so on. So if you notice the terms of this special power series, it has the variable x, x squared, x to the third, and so on. What this does is it describes a polynomial. Okay? So these are polynomials. For example, let's just say I was looking at a sum from 0 to 2, something like 2 plus 3x plus 5x squared. This is a polynomial where the 2 would be my c sub 0, 3 is the c sub 1, 5 is my c sub 2. So these c values are all coefficients for my polynomial. And here we say that it has a center 0. And it has a center 0 because if I let x be equal to 0, then notice in the series, all the x's, all the terms that have x in them will go away, and all I have left is that constant c sub 0. But the center can actually be anything. Now, if we look at this next series, where you see the x minus a, that just means we've shifted our polynomial. We've changed our center. Our center is now a. So instead of having x, x squared, and so on, we have x minus a squared, and so on. But notice that that property still holds, that if I let x be equal to my center a, then all the terms will go to 0 except for the constant term. Next, what I'd like to do is review linear approximations from Calc 1. I don't know if you recall our linear approximations. Those were tangent lines that we used to approximate values for functions. Let's go ahead and look at this graph. Let's say that this curve represents some graph f. And let's just say that I have some x value between 1 and 2, and I want to find the y value on this curve. Well, oftentimes graphs that have a lot of curves are really hard to work with. So one strategy we used from calculus was to take some nice value. So if I look at this, 2 is close to my x. And then drop a tangent line at that value, so that if we put that x value into the equation of our tangent line, it'll give us an approximate value for that function evaluated at that x value, because look at those y values, they're very close in value. Remember, the equation of a line is just y minus y sub 1 equal to mx minus x sub 1. And here, this point that I'm looking at that's common to both my tangent line and my function, I'm going to call this point, which in this graph is 2, I'm going to call that A. So this point that they share in common is the point A comma f of A. Oops, need parentheses around that, which means my x sub 1 is a, my y sub 1 is f of a. And this equation becomes y minus f of a equal to our slope x minus a. The slope of our tangent line is simply the derivative. So our slope is equal to the derivative at that point a. My equation is y minus f of a equal to f prime of a times x minus a. Now if I simply add f of a to both sides, I can isolate my y value to write f of a plus f prime of a times x minus a. And hopefully this is looking familiar to you, because all we have to do now is just substitute our linear approximation notation L of x for the y value, and we have our linear approximation, which is simply the equation of our tangent line. So if I put in x values, and in our case our a value is 2, but that's not important. So if I put in x values near that value a, my linear approximation will be approximately equal to the value of the function, which is the whole point. Oftentimes the function is very hard to work with, especially if you don't have any technology such as a calculator. So a nice thing you could do is drop a tangent line, use your linear approximation. The problem becomes as we get further away from our nice point. So notice that if I'm getting closer to 1, and I look at the point on my curve and compare it to the point on my tangent line, they're starting to get further and further apart. So my linear approximation is only good for values very near that a value that I chose. However, look at this curve. And I'm going to go back to my point A. It would be really nice if I could simply drop in a parabola and use that parabola as an approximation, because parabolas are also very nice to work with. They're just second degree polynomials. So notice that the parabola and my curve, it looks like the point matches exactly. And here I'm just referring to that second x value. So maybe a quadratic approximation would be more appropriate as we get further away from this a value. So this linear approximation, this is just an equation of a tangent line. It's linear, it is a polynomial, but it's a polynomial of degree 1. So I'm going to replace this linear notation with p sub 1 for polynomial of degree 1. And my quadratic approximation, I'm going to call that p sub 2 for a polynomial of second degree. Going back to our power series, notice that p sub 1 of x is going to be the summation from k is equal to 0 to 1 of c sub k. And in our case, our center is not 0, it's 2. So this becomes x minus a, which is 2, to the k power. So our linear approximation in this particular example can be written as this power series. If I expand it out, it'll be c sub 0 plus c sub 1 times x minus 2. K is just 1. So something to notice is that p sub 1 of the center 2 is going to give me my c sub 0. If I look at the quadratic approximation, that will be written in terms of the power series as k is equal to 0 to 2, because it's the second degree, of c sub k x minus 2 to the k. Expanding out, I have c sub 0 plus c sub 1, x minus 2 plus c sub 2, x minus 2 squared. Also note that if I take p sub 2 of the center 2, all the terms go to 0 except for that first constant term. So any polynomial can be written as a power series. We just have to figure out what these coefficients are. So that brings me to this box at the bottom. This is the linear and quadratic approximations. So our p sub 1 is f of a plus f prime of a times x minus a. P sub 2 will turn out to be f of a plus f prime of a times x minus a, plus the second derivative at our center a divided by 2 times x minus a squared. So this f of a, that's going to be our c sub 0. The f prime of a is the c sub 1. The f double prime of a over 2, that's our c sub 2. So it's this whole coefficient on the x minus a, the whole coefficient, the whole coefficient. Something else you should note is that if we look at p sub 2 and you look at these first terms, that's actually p sub 1. So if you already have your linear approximation p sub 1, you can easily get p sub 2 by just taking your p sub 1 and then figuring out that next term. Now let's look at an application of using our linear and our quadratic approximations. In example 1, we have this function e to the negative x. And in this section, I'm not going to focus on very complicated functions. It's just something like e to the x or cosine of x and so on. Part A says find the linear approximation at x is equal to 0. So when your MyMathLab or textbook says to find the approximation at some x value, what they're giving you is the center. So that means your a value, which is your center, is equal to 0. Part B says find the quadratic approximation at x is equal to 0. And then for C, we're going to use parts A and B to approximate the value of e to the negative 0.1. So part A, the linear approximation, p sub 1 of x is f of 0 plus f prime of 0 times x minus 0. So that would be the basic form, which means p sub 1 of x is equal to, so f of 0, if x is 0, e to the 0 is just 1, plus, what is f prime of 0? So it might be helpful if off to the side, we figure out what the first derivative is, which is going to be negative e to the negative x. But also part B, we're using a quadratic approximation, which means we're going up to the second derivative. And the second derivative is just e to the negative x. So evaluating that first derivative at 0, we get negative 1. So plus negative 1 times x because a is 0. Or in other words, our linear approximation is going to be 1 minus x. Part B, we're going to find the quadratic approximation, p sub 2. So notice that that's actually p sub 1 of x plus the second derivative evaluated at our a value of 0 over 2 times x minus 0 squared. So p sub 2 of x is equal to p sub 1 was 1 minus x plus the second derivative evaluated at 0 is just e to the 0, which is 1. So this becomes 1/2 x squared. In part C, we're going to use both our linear and our quadratic approximation to estimate the value of e to the negative 0.1. So the x value that we're going to be using is positive 0.1. Our linear approximation at 0.1 is 1 minus 0.1, which is simply 0.9. And the quadratic approximation is going to be 0.9, because it's p sub 1, plus the 0.1 squared over 2, which is going to be 0.905. That answers part A, B, and C, but just for our own information, just notice that e to the negative 0.1 in our calculator is approximately 0.90483. I'll kind of stop there. Notice that both of these approximations are very close. It turns out that the higher the degree of polynomial, because we can also create a cubic polynomial, fourth degree polynomial, the higher the degree, typically it's a more accurate estimation. That's going to bring us to our Taylor polynomial. So a Taylor polynomial is looking at a polynomial of any degree. So not just linear and quadratic. So let's say we have a function and all its derivatives are defined at some point A. Then we can define our Taylor polynomial as this p sub n, and here I'm looking down at that long string of stuff, as p sub n of x, so for any degree n, f of a over 0 factorial x minus a to the 0 power, plus f prime of a 1 factorial over 1 factorial times x minus a to the 1, plus f double prime of a over 2 factorial times x minus a squared, plus, and so on. So there's this very, very nice pattern when we're dealing with our Taylor polynomials. Notice here that the first term has no derivative, so I'm just going to call that the zero derivative. It's over 0 factorial, and the x minus a is to the 0 power. The second term is that first derivative. It's over 1 factorial, and the x minus a is to the 1 power. The next term is our second derivative. It's over 2 factorial. The x minus a is squared. So in general, whatever power or whatever derivative this is, whatever nth derivative, it's going to be n factorial, x minus a to the n. And notice if we were to simplify that, 0 factorial is just 1, 1 factorial is 1, 2 factorial is 2, which is where we got that divide by 2 when we're looking at the quadratic approximation. So compactly, we can write it as this power series down here. And we can define our c sub k's as the kth derivative at a over k factorial. So let's go back up to these p sub n of a's. What is that about? So p sub n for any order polynomial, p sub n evaluated at a is just f of a. So maybe down below, I'll verify this with p sub 1. So p sub 1 of x is equal to f of a plus f prime of a, x minus a. So clearly I don't want to erase it, it takes too much time. So clearly p sub 1 of a, if you put in a for x, the term with the derivative goes away and you just have f of a. Well, what about p sub 1 prime, the first derivative? So if we take the derivative of f of a, that's just a constant, it's 0. And then when we look at f prime of a times x minus a, we have to use the product rule. So it's going to be the second derivative at a. So derivative keep plus keep. Derivative of x minus a is simply 1. Now if we look at the first derivative of p sub 1 evaluated at a, the x minus a term goes away, that's 0. That first term was 0. What we're left with is f prime evaluated at a. And we can do this for any number of derivatives, which is where that property p of n of a is f of a, p prime of a is f prime of a, p to the nth derivative is equal to f of the nth derivative at a. Let's look at another example. Let's say we have cosine of x, and we want to find the nth order Taylor polynomial centered at 0, which is nice because that's going to be our a value, for n is equal to 0, 1, 2, and 3. So I'm going to have to figure out 4 of these different polynomials. Notice that I'm going up to n is equal to 3, so that's a third degree polynomial. That tells me I'm going to need a third derivative. So right away what I'm going to do, before I even figure out the polynomials, is I'm just going to go ahead and write down up to the third derivative. F prime of x is negative sine. Second derivative is negative cosine. Third derivative is sine. And now in part A, I need to find 4 polynomials. The first polynomial would be when n is equal to 0. So that would be p sub 0 of x. P sub 0 of x is simply equal to f of my center, which is 0. So remember my a, which is the center, is 0. So p sub 0 of x is going to be cosine of 0, which is 1. When n is equal to 1, I'm finding the first degree polynomial. And the first degree polynomial is going to be f of 0 plus f prime of 0 times x minus a, which in our case is 0. And that's just 1, because the first derivative is negative sine evaluated when x is equal to 0. It just gives us 0. P sub 1 of x is also simply equal to 1. When n is equal to 2, I'm looking at the second degree Taylor polynomial, which would simply be p sub 1 of x plus the second derivative evaluated at 0 over 2x minus 0 squared. P sub 1 was 1. The second derivative evaluated at 0 would be negative 1. So this is actually going to be a minus, and then the x squared, so minus x squared over 2. When n is equal to 3, my third degree Taylor polynomial is my second degree Taylor polynomial plus the next term, which is the third derivative evaluated at the center over 3 factorial, which is 6. And then this is x minus the center to the third power. So my third degree polynomial is going to be 1 minus x squared over 2. So the third derivative is sine, evaluated at 0 is 0, so that term is gone. So notice that my 0 and my 1 degree polynomials were the same. My second and my third degree polynomials were the same. So I found all of those polynomials. Now I'm going to go to B, which is graph the function at the center along with these Taylor polynomials. So I'll just do that right here. Well, that's kind of off. I don't think I need that to be as long as it is. Let's see, so cosine does something like that. So that would be my function. And then p sub 0 is 1, which just means it's the horizontal line. And then p sub 1 is also the same. So these guys are the same. Notice that this is just a sketch. I'm not getting all crazy about it. And then look at p sub 2, p sub 3. That would be a polynomial. It's going to be a little bit skinnier than the cosine function, and you can go ahead and verify this by putting it in your calculator. Again, this is just a sketch. So p sub 2 and p sub 3, those would be the same graphs. So notice that this quadratic approximation and the third degree approximation, which are exactly the same, would be more accurate when we're looking at approximating values of cosine. That was part B. Part C says use the polynomials to approximate cosine of negative 0.2. So for C, the x value that we're going to use is negative 0.2, since our function is cosine. P sub 0 of negative 0.2, that's the same as P sub 1 of negative 0.2. And that's just going to be 1. P sub 2 at negative 0.2 is equal to P sub 3 of negative 0.2. And that's going to be 1 minus negative 0.2 squared over 2. That turns into 0.98. So we're supposed to find the absolute error. Well, I can easily see what the error is when I'm looking at P sub 0 and P sub 1. That error is simply cosine in your calculator of negative 0.2 minus 1. And then the error with the other two would be cosine of negative 0.2 minus 0.98. So the error here, well, actually I'm going to use an approximation because I'm just plugging this into my calculator. Let's see, I get 0.01993. I'll go that far. And then looking at the error when we compute using p sub 2, p sub 3, it looks like 0.00007. 1, 2, 3, 4. Yeah, that's right. So it's clear that the higher the degree, the more accurate the approximation in this particular case. Now this, let's do another example. In this example, it's not specific. It says for us to use Taylor polynomials, and it tells us what degree to use, 0, 1, 2, 3, and 4, to approximate the square root of 5. But notice that it's not giving us a center. It's actually not even giving us a function. And to use Taylor polynomials, you need a function. And then we're going to compare the actual value to our approximations. In this particular example, we need to first define a function. Since we're looking at approximating the square root of 5, it seems reasonable that I'm going to let my function be the square root function. But this is not unique. You could use anything you want. Let's see. So I have to find a center. Notice that I'm approximating the square root of 5. So I want to choose my center so that it's close to 5, but it's a nice number when I put it into my function. So I'm going to choose for my center a equal to 4, because the square root of 4 is a nice number. It's 2. Now I could have chosen a equal to 9, but that's further away from 5. Okay? So the x value that we're going to be approximating in our function is 5. Since I'm going up to a third degree Taylor polynomial, I need to go up to my third derivative. I'm going to do that right now. My first derivative, notice that this is x to the 1/2. So this is going to be 1/2 x to the negative 1/2. Second derivative will be negative 1/4 x to the negative 3/2. Third derivative is 3/8 x to the negative 5/2. While I'm at it, I think I'm just going to evaluate my f of a, f prime of a, and so on. So f of 4 is 2. The first derivative evaluated at 4 should be 1/2 times 1/2 should be 1/4. The second derivative evaluated at 4 should be negative 1/4 times 1 over the square root of 4 to the third. I'm just going to plug that in my calculator and hit my fraction key to get negative 1 over 32. I'm going to do the same for the third derivative, evaluated at 4. Put it in my calculator, hit the fraction key, I get 3 over 256. I'm not going to write that as a decimal because I want to have nice, clean, exact answers for now. So my p sub 0, that would be when n is equal to 0. That's just f of 4, which is 2. My p sub 1 is going to be p sub 0, which is 2, plus the first derivative evaluated at 4 times x minus 4. So this is going to be 2 plus 1/4 times x minus 4. If I distribute that 1/4, I get 2 plus, I'm going to write it as x over 4 minus 1. So it looks like my first order Taylor polynomial is simply 1 plus x over 4. All right, second degree is the first degree, 1 plus x over 4, plus the next term in my series, which would be the second derivative evaluated at 4 over 2 factorial, which is 2, times x minus 4 squared. And then that would be 1 plus x over 4. Looks like it's going to be negative 1 over 64, so minus 1 over 64 x minus 4 squared. And I don't think I'm going to multiply that out, distribute, and combine like terms. I'm kind of lazy right now. I'll just stop there. And our third would be 1 plus 1/4 x minus 1 over 64 x minus 4 squared, plus our next term, which is going to be the third derivative evaluated at 4 over 3 factorial, which is 6, times x minus 4 to the third. So I get 1 plus 1/4 x minus 1 over 64 x minus 4 squared. The fourth derivative, let me go back up to here. It's going to be divided by 6, so it's going to be times 1 over 6. The 3's cancel, and I get 1 over 512. So plus 1 over 512 times x minus 4 to the third. So that would be my third degree polynomial. So I found all 4 of those actually, polynomials. And now I need to approximate the square root of 5. P sub 0 of 5 is 2. P sub 1 of 5 is 1 plus 5 over 4, which is 9 over 4. Now I am going to write this as the decimal 2.25 because I want to see how close it's getting to the approximation. P sub 2 of 5, that's going to be my 2.25, my P sub 1, plus that last term, which is minus 1 over 64. Whoops. And then that would be 143 over 64. It's going to be approximately 2.2344. I'm going to take it out to 4 decimal places because in the instructions it says then compare to the actual value of the square root of 5 rounded to 4 decimal places. P sub 3 of 5. If I plug that in the calculator, I'm adding to the 2.25 minus 1 over 64. I'm adding 1 over 512, right? Because I'm putting in 5 for x in the polynomial. The 5 minus 4 is just 1. So that should be 1145 over 512, which is approximately equal to 2.2363. When I compute the error in the first one is clearly, well, maybe not clearly because I forgot to write down that the square root of 5 in my calculator is approximately equal to 2.2361. So the error for the first estimation, P sub 0, is 0.2361. P sub 1, if I compute the error, I get 0.139. P sub 2, I get 0.017. Looks like the error is getting smaller. And then at P sub 3, I get 0.002. So this idea of error brings us back to our remainders, and this is similar to the remainders we talked about when we looked at Simpson's rule. And midpoint and trapezoid is the same error that we talked about when we're looking at our previous chapter 10 in sequences. So if you're looking at any nth degree polynomial, it's just going to be an approximation. So if you take your function and you subtract your p sub n, your approximation, what's left over is your remainder. So note that if you did take the absolute value of the remainder, you get error. Now let's look at Taylor's theorem, and this is often referred to as Taylor's remainder theorem. We'll take that previous equation from our definition, and we'll just solve that equation for our function. So our function is always equal to the Taylor polynomial plus its remainder, where the remainder is specifically equal to this awful expression. Now this awful expression comes from our previous chapter. Remember when we were talking about a remainder being less than the a sub n plus 1 term? Well, if you look at your Taylor series, the n plus 1 term corresponds to the n plus 1 derivative. So, oops, sorry, I always forget to do that. So when we look at this remainder and how we define it, it's kind of based on that n plus 1 term, which in our case is this n plus 1 derivative over the n plus 1 factorial times the x minus a to the n plus 1 power. Notice that we have this c value here. And this c value, it's not the same as that x value, because our remainder is going to be equal to this expression for some c value between our center A and our x value that we're approximating. So we don't really know what that c value is, but we know that that's what our remainder will equal to for some c value there. Oftentimes it's helpful to find a formula for the remainder, because if you do have the formula for your remainder, you can simply put in values to see the smaller the remainder, the more accurate your approximation. So you can use that to do your approximations. Example 4, we have our function again, e to the negative x. Our center is 0. We want to find the remainder term for a general value of n. And since this says a general value of n, we're not going to be specifically computing the 0, the 1, the 2, the third degree polynomial, and so on. But in order for us to find a general formula for the remainder term, what we first want to do is we want to find a pattern for the n plus 1 derivative, because that's how we define our remainder term. So what I'm going to do is I'm just going to start writing out the derivatives of e to the negative x. So the first derivative, negative e to the negative x. Second derivative would be e to the negative x. Third derivative, negative e to the negative x. And I could keep going. My fourth derivative is e to the negative x. But it's really not necessary because I see the pattern here. If I look at the n plus 1 derivative, with respect to any x value, it looks like it's going to be equal to, it alternates, so there's going to be a -1 times e to the negative x. I just have to figure out what the exponent is on my -1. So remember, the first derivative corresponds to n is equal to 1. So when n is 1, it's negative. N is 2, it's positive, and so on. So if you look at the pattern here, look at these n values. Notice that this is a -1, this is a +1, this is a -1, this is a +1. So if I wrote this first derivative as -1 to the 1 power e to the negative x, it's still true. If I wrote the second derivative as -1 squared e to the negative x, that defines the second derivative. So going back to our sequences and finding patterns, can also find a pattern sometimes when you're looking at defining the remainder for any n value. So it looks like that whatever n I'm putting in is going to correspond to the exponent on my -1, which means I can define the n plus 1 derivative as -1 to the n plus 1 power times e to the negative x. So once I've defined my pattern and I found my definition for the n plus 1 derivative, I can define my remainder for any nth degree polynomial as being -1 to the n plus 1 e to the negative c, I'm not putting x in there, over n plus 1 factorial times, and here my center is 0, so this is simply x to the n plus 1. Sometimes it's very difficult to find a definition for the remainder. Although this is not part of the problem, let's just consider f of x equal to the cosine of x. So if I was looking at the derivatives, I would have negative sine, second derivative is negative cosine, third derivative is sine, and I'll go to the fourth derivative. It's cosine. I'm kind of back to where I started from. But the problem is, since it's alternating between sines and cosines, it's very difficult for me to define the n plus 1. So I do notice that when I look at the n plus 1 derivative, I do notice that it's either going to be plus or minus cosine, or it'll be plus or minus sine. And it looks like if n is odd, or if n is even, I'll have different values for my derivative. So again, if n is equal to 1, I end up with a sine. If n is equal to 2, I end up with cosine. If n is equal to 3, I end up with sine. If n is equal to 4, I end up with cosine. So I end up with cosine if the derivative is even. I end up with sine if the derivative is odd. when you're looking at the n plus 1, if n is odd, notice because it's the n plus 1, put in an odd number for n. This is actually an even derivative. And it's going to be plus or minus sign when n is even in this particular definition. So that's very difficult to write the remainder term. So sometimes it's not really efficient to write the remainder term, and sometimes it is. It just depends on the function you have. So now let's go into estimating the remainder. Notice that we have an absolute value in this theorem. That absolute value is there because when you take the absolute value of the remainder, and I know I've said this so many times, that's your error. This next theorem is very helpful when you want to figure out a bound on your error, or what is the largest value of the error. So this error, and this is the only thing I'm concerned with here, it's going to be less than or equal to this value m. And this is kind of going back to those error formulas again for midpoint trapezoid Simpson, where you have to find this value. It's going to be less than or equal to this m value times the absolute value of x minus a to the n plus 1 over the n plus 1 factorial. Very similar to our previous theorem, and in fact, that is where we get this theorem from, the previous theorem. So the goal here is when you're trying to find a bound on your error, the goal is to find this value m, because you should have the a value, your center. And that's where you're going to look at how m is defined. So our m has to be greater than or equal to the absolute value of the n plus 1 derivative at c. C is between x and a, including a and including x. So the idea is to compute the n plus 1 derivative. Think of all the values between your center a and the x value for your approximation. And then your m value will be larger or equal to the largest that that could possibly be. Let's look at an example. In example 5, we have our function e to the negative x. Here, I'm only concerned with my center a equal to 0. I'm going to use the remainder term to estimate the absolute error. And when we say absolute error, that's referring to the absolute value of the remainder of e to the negative 0.5 when n is equal to 4. So we're given a lot of information here. We know our n value is 4. So we're going to look at the absolute value of r sub 4 of x. And we know that that has to be less than or equal to this m value that we're going to find. Since our center a is 0, this becomes the absolute value of x to the n is 4, so the n plus 1 is the 5th power, all over 5 factorial. And then 5 factorial is simply 120. So I'm going to go ahead and write 120 down here. My goal is to find this m value. So that means I have to compute my 5th derivative, which I already know from my previous example is negative e to the negative x. So remember, my m has to be larger than anything that this can be, negative e to the negative I'll put in C. For any C in the interval from A to X. The X value that I'm approximating is e to the negative 0.5, so it's 0.5. And my A value is 0. So I'm looking at C values between 0 and 0.5, because that's the X value that I'm approximating, and the 0 is my A value. So I have to look at this absolute value of negative e to the negative c and think about putting in c values from 0 to 0.5. It might be easier if you just graph that absolute value, or if you simply take away the negative, because it is an absolute value, and e to the negative c becomes 1 over e to the c. So 1 over e to the c, as the c values get larger and larger and larger, that fraction is getting smaller and smaller and smaller. So e to the c, when c is equal to 0, is simply 1. So 1 over e to the c, if c is 0.5, is going to give you something that's smaller. So it's going to be at its largest when c is equal to 0. So this absolute value is at its largest when c is equal to 0, which means it's e to the 0 power. It's just the absolute value of 1. Your m has to be equal to that or larger, so it makes sense to choose m equal to 1. This is not unique. M equal to 1 works, but so will any m larger than 1. Because remember, we're just trying to figure out the largest our error could be. However, if I do choose m equal to 1, then this absolute error is going to be absolute value of x to the 5 over 120. And my x value that I'm approximating is 0.5. So notice if my x value is negative, I still have to take the absolute values of that, so I would turn it to positive, but I don't have to worry about that because my x value is simply 0.5 to the 5 power over 120. So when we put that in our calculator, we get 0.00026. And that's our error. In this last example, we're still trying to find an error. We're using the same formula that we did in the last example. The reason why I want to look at this example is because it's worded a little bit differently, and there's a lot of information that's actually missing in this problem. So we have to sort of figure out what all our values are, such as the center A or the N. In example 6, it just tells us to estimate the maximum error on this given interval. And then it tells us in general, error bounds are not unique. Okay, that's fine. You can always choose a larger m value. That makes sense. The problem is we're not given an x value to approximate. We're just given this interval, which means that when we figure out the error, we have to assume it's for any x value in the interval from -1/2 to +1/2. Now we are given a function, which is just e to the x. So we could figure out the Taylor polynomial, any n-degree Taylor polynomial, but instead let's look at this approximation that we're given. We're being told that e to the x is approximately equal to 1 plus x squared over 2. Well, that should look familiar to you because that is a second degree Taylor polynomial when we're looking at e to the x. So since this is p sub 2 of x, then that tells me my n is 2 because your n is always the degree of the polynomial. And it also tells me something more. Notice that this is just x and x squared. It's not x minus a squared. So that tells me my center a is probably 0. But there's another way that I could figure out what my center is, and that's by the interval that I was given. The middle of negative half and positive half is 0. So that's going to be our center. So I can confirm my center by looking at that interval, and I can also confirm my center by looking at the second degree Taylor polynomial that was given to me. So I now know my absolute value of my remainder, which is r sub 2, for the n is equal to 2, has to be less than or equal to m, which I need to find, times the absolute value of x minus 0, so absolute value of x to the n plus 1 power, which is 3, over 3 factorial, which is 6. I need to find my m, so recall that my m is going to be greater than or equal to the n plus 1 derivative of my function. But my function is just e to the x. First derivative is e to the x. Second derivative is e to the x. All the derivatives are e to the x. Sorry, this is supposed to be, I was going to write x, but it's a c. So my m that I'm choosing has to be greater than or equal to the absolute value of e to the c for any c value in the interval that I was given. Now the exponential function goes from small to large. So I can just look at this and go, oh, this absolute value should be its largest when x is equal to 1/2. So let's go ahead and look at this graph of our exponential. At negative 1/2 and at positive 1/2. So since this function grows small to large, and you can verify this by using your calculator, that means that the c value that I'm going to choose is 1/2. That's when the absolute value of e to the c is at its largest. So that means that I can choose m greater than or equal to e to the 1/2. So I'm going to choose m equal to e to the 1/2. My remainder is going to be less than or equal to e to the 1/2, absolute value of x to the 3rd power over 6. Well, that's fine, but remember I'm supposed to find a bound on my error. What is my x value? Again, I don't know. I have to look at all the x values in that interval. Notice that at negative 1/2, if I take the absolute value, then I have positive 1/2 to the 3rd, which is 1/8. If I choose any other x values, getting closer and closer to 0, so if I had, say, 1/3, that fraction's actually getting smaller. My largest value would be when x is equal to negative 1/2 or x is equal to positive 1/2, since I'm taking the absolute value. So this error is going to be bounded by e to the 1/2, 1/2 to the 3rd. Doesn't matter if you choose the negative or the positive, over 6. which is going to be e to the 1/2 over 1/8 divided by 6. It looks like 48 over 48. This will be the bound on my error, and that would be approximately equal to 0.0343. You might want to verify that. So again, it's just slightly different from the previous example. In the previous example, we were given a specific x value that we wanted to approximate. This says, what is the most the error could be if you choose any x value in this interval using a second degree Taylor polynomial? So if I choose any x value and my approximation is with a second degree Taylor polynomial, at most the error would be 0.0343, which is pretty good. Now let's just go for a second. This question actually is done, but I'd like to look at this note. Error bounds are not unique. I chose m equal to e to the 1/2. That's actually not a very nice number. So I could have chose a larger m value. It would still give me a bound on my error. So notice that e is approximately 2.72, so this is approximately equal to the square root of 2.72. And that's going to be less than the square root of 3, which again is less than the square root of something nice, which would be the square root of 4. So instead of choosing e to the 1/2 to be my m, I could have chosen this larger value of 2. And if I chose that larger value of 2, then my error is going to be less than or equal to 2 over 48. So that's what it should turn out to be. Which 1 over, yeah, let's see, that's approximately 0.0417. So notice that if I chose a larger m value, I know that my error has to be less than 0.0417, which is fine. If I chose a m value closer to something a little bit more accurate, then I get a nicer bound on my error. But it really doesn't matter. You're just trying to figure out some bound on your error. So if you were to do an approximation, maybe if this error is too big, you can adjust, use a polynomial of higher order would be the most appropriate next step. And that's it for this section.